Okay, this video is going to be about the conservation of energy and non-conservative work. Okay, so first off, we're going to go through a little bit about the types of energy that we're talking about. Now, there's all types of energy: heat energy, I was going to say thermal, but electromagnetic, and so forth and so forth.
Morning Mass is about to begin in the chapel. We'd love to have you there. Thank you.
Okay, this video is going to be about conservation of energy and non-conservative work. Now, first off, I'm going to start by talking about some of the types of energy that we're going to be dealing with. Now, there's all types of energy, right? You have heat energy, you have electromagnetic, and so forth and so forth. But we're going to be focusing on mechanical energy for these problems that we're going to be doing here in future videos. So, first off, if we have an object, a mass, that's located above the ground, we say that it has potential, and that's equal to mgh. That's potential energy due to gravity. If we have, so it's going to fall down. If we have an object that's rolling in this direction and it's moving, we say that it has kinetic energy, and that's 1/2 mv squared. Okay, that's really it. I mean, it's basically really simple stuff. Now, the other one is a potential energy in a spring. And let's say that we take a spring and we have an object next to it, and we take it and we push it back and compress it. I think we'd all agree, if you were playing pinball and you pull the little plunger back, that energy is stored up in there, and it's potential because it has the potential to do something on the object. And we know that the potential energy in the spring is equal to 1/2 kx squared. Now, I haven't actually dealt with that equation in a little while, but that's it. Okay? And so, whenever we're talking about mechanical energy, we need to look at all of these things. All right? And so, first off, we're going to define conservation of energy. So, conservation of energy, it seems like every law in science says the same thing, right? Things cannot be created, they cannot be destroyed. Same thing as energy. And energy may be more importantly than anything else, because without it, nothing else is really there. So what we're going to do is we're going to look at initials and finals. Okay? And so really what we're talking about is the sum of the energy initially should equal, or will equal, the sum of the energy. See how messy that gets. At the end. Now, sometimes you might see that written with an ME for mechanical energy, and that's fine. But just simple energy is good. So if I take a look at all of these, we have the possibility of having all of these all at once in a problem. Okay? I'm going to write every single one out. So potential energy initial due to gravity plus potential energy initial due to a spring plus the kinetic energy initial will equal the potential energy final due to gravity plus the potential energy final due to a spring plus the kinetic energy final. Now, I will not give that on test. I think if I give that, it defeats the purpose of understanding what conservation of energy is. Okay? So let's just look at a real simple type of problem. And so we can go through this and kind of take a look. All right. Let's say we have an object on an incline, a mass here, and we want to know the final velocity here. Okay. So I have the ball, I'm holding it, I let go, it starts to roll down, and we want to know what the velocity is at the end. Now, in the past, when we did these problems, we'd have to know the angle. We'd have to figure out the acceleration. Nice thing about energy is we don't care. We don't care about those things. We care about the energy at the beginning and the energy at the end. And so I'm going to work through this equation, and I'm not going to cross things out because I want to use it again. So I'm going to go through these, and I'm going to say, okay, what kind of energy do I have here? Do I have potential energy due to gravity? Yes, I do, because it can go down. Do I have potential energy in a spring? I see no springs anywhere. So you know what? Let's get rid of this one too. Is it moving at the beginning? Some students will say, yeah, you let it go, it's moving. When I let it go, it's not moving at first. So we have no kinetic energy. All right. Now let's look at the final part at the end. Can it be any higher off the ground? No. But is it moving? Yes. So here's what we do. We say that potential energy is equal to the kinetic energy. And it's real simple, right? If I take a look at these equations over here, mgh 1/2 mv squared. We'd be solving for this right here. You would notice that the mass cancel out. And I'll probably say this multiple times. You'd hear me say it in class all the time, that if we don't have friction, the mass doesn't really seem to matter. Mass is important in friction because it makes the normal, right? The amount of force that the ground is pushing up on the object with. And so it should cancel out most of the time. In this case, you could solve for VF. I'm not going to because I don't want to write that equation down. And I reference it in another video on why. But you're going to use that a lot. All right. So I mentioned friction. See this non-conservative work? Non-conservative work means that there's friction involved. Okay? So if I have a ball rolling and there's friction, what's the ball going to do? It's going to stop. Okay? If I have an object that's falling straight down and I find the final velocity, if there's air friction, what's going to happen? The final velocity would be less. All right? So it matters. Now, a lot of times, like, you'll catch me saying, and you'll probably hear other teachers say, energy lost. Okay, and you'll say, wait a second, conservation of energy, no energy is ever lost. That's true, it's not. So when we say lost, we more or less mean that the mechanical energy is lost, okay? And so if there's friction, it's turned into heat or some other type of energy, but the mechanical energy is not as much as it used to be. And so here's my question. What side would you add it to? That energy that's lost, would you add it to the initial side or would you add it to the final side? Now think about it. It's lost, right? It's gone. It's changed to something else, and we're looking at mechanical. We would add, hopefully that's on the screen, we would add that to the final side, okay? And so you'll notice there, I wrote WNC, non-conservative NC work. These are fun to erase, as you can see, my wobbly board. All right, so WNC stands for non-conservative work. Okay, we would add it to this side, the final side, if we had to. And do you remember that work is equal to the force times the change in displacement? Right? So guess what? What's the force when we're talking about friction? It's friction. And it's still multiplied by the change in x. So really this, work is still work, F times x. The question is, what F are we talking about? In the non-conservative work, we're talking about friction. Okay? So sometimes in these problems, they'll say, oh, how much friction is there? Okay, or what's the final velocity? When it asks those kinds of questions and there's friction involved, it has to give you a little bit more information. Okay, maybe it gives you the final velocity. Maybe it gives you the length of the track. But you have to be careful, okay, when you solve those. You can't go back to doing it the way that you did without friction. It doesn't work that easy anymore. Remember how I talked about the mass canceling out? Well, look, if we put non-conservative work in here, there's no mass. So you can't cancel out mass anymore. Mass is very important. So you just need to be very careful in solving those types of problems, okay? So this is a video on the conservation of energy, which is right here, the equation, and how friction and work is involved in that.